This is part 2 of our force diagrams revision, specifically focusing on connected particles. And in this situation, I've got one of my particles on a slope, but the same principles of connected particles apply. My advice with these sorts of questions, especially because of this piece of information that I've highlighted there, the tan alpha is 4/3, is to write down everything that you've got information-wise first. And also don't forget your diagram. So we want to draw out the diagram for ourselves as well. So start with that tan alpha. If tan alpha is 4/3, we can work out what sine alpha and cos alpha will be. And they're more useful to me because those are what I'm going to end up having when I resolve my weight force. The reason they've given it to you as a fraction like this is because they're going to want you to keep it as exact values. So we're going to, instead of going for what alpha is and doing tan to the -1 or inverse tan, we're going to draw a triangle instead. So here's a right angled triangle. Tan, of course, is opposite over adjacent. So our opposite side is 4, our adjacent side is 3, and that will give us a hypotenuse of 5, which would mean that sine alpha, which is opposite over hypotenuse, is 4/5, and cos alpha, which is adjacent over hypotenuse, is 3/5. Also from the question, we know that mu is 0.4, it's the coefficient of friction, and so we can write down that friction is mu r, or 0.5 r, and we'll have to find a value for r at some point. Okay, drawing our diagram out then. So we've got our two particles. Let's focus on Q for a start. Q is 0.5 kilograms, so it'll be 0.5 G heading downwards. We know that we've got tension sort of pulling it upwards, if you like. The pulley is also experiencing tension at that point straight down. And that's all we've got going on with Q force-wise, except for, of course, that this thing is going to be accelerating, and we just need to read the rest of the question to figure out which way that is going. Particle Q won't hit the pulley because particle P slides down the plane, so this bit is going up here. Particle P then is going down the plane, which means that friction is acting up the plane, and so is tension. The pulley is experiencing tension going downwards. We're on a surface here, so the reaction force, or rather the normal reaction force, will be perpendicular to the slope, and we have a weight force of 4G. That's great. Our reaction force, our friction and our tension, they're perpendicular to one another. Our weight is not acting in that same perpendicular plane, so we need to resolve it. There is, making up this weight force, an amount that acts exactly opposite to R, so essentially sticks it to the slope, if you like, and an amount of the force that will encourage it down the slope. We just need to figure out what those two are. Now, I'm just going to move that down the slope force, if you like, to the end of this triangle shape that I'm making here. Now, don't forget, we tend to draw force arrows out of the particle, which is why we move it up to where I drew it originally, but we can think about it as the three sides of a triangle, with 4G being on the hypotenuse. Since this is orientated at an angle of alpha, the angle alpha will appear in here, and that makes this blue line sticking it to the slope 4G cos alpha, and we know cos alpha is 3/5, so that's quite nice, and the bit sliding it down the slope is 4G sine alpha. I have now resolved this 4G force. I've split it up into its components. So I put brackets and a line through it, and I somewhere just say to my examiner that that means I've resolved that force, just so they can follow the working. Part A then asks us to find the tension in the string during the motion. Well, again, we've got all sorts of things that we don't know, so we're going to try and create as many equations as possible. If we just begin looking at Q, we're going to do exactly what we did last video, which is just draw out a little diagram for Q on its own. So Q is experiencing tension going up, its weight going down, and it is moving upwards. So our acceleration arrow will be acting up. Since we are in motion, we're going to be using Newton's second law, so F equals ma, and I'm going to take up to be my positive direction since that's the way we're moving. Tension is encouraging it up, the weight is trying to slow it down. Our mass is 0.5 and we don't know our acceleration. There is our first equation. That's all I can create from Q because there's no other dimensions. So if I just look now at P, I've got a particle sat on a slope. Essentially, that's all I've got. So we said we've got tension and friction acting up, the component of the weight acting down, part of the weight acting into the slope, and our normal reaction opposing that. That's what we've got going on for P. Now, if we look at this direction, so perpendicular to the slope, my particle isn't crashing into the slope and it's not bouncing off of the slope, it's in equilibrium in that dimension. So we're actually dealing with an equilibrium problem when we look at R and this 4g cos alpha, which means that 4g cos alpha must equal R. Otherwise, the particle would bounce off of the surface or it would sort of get dug into the surface. Neither of those things are happening. Okay, good. So we've got two equations. We have got so far one equation from Q, one equation from P. There is another equation that we can create in P. This particle is moving down the slope, which means that we can apply F equals ma, and our positive direction will be down the slope. So we've got 4g sine alpha trying to drag it down the slope. Tension is slowing it down. Friction is slowing it down. So those two should be as negatives. The mass is 4 and acceleration we don't know. There is a third equation. Now hopefully we've got enough information to be able to solve this problem. We just need to substitute everything. We're trying to find the tension, so we're going to substitute what A is, our acceleration. So if we just go back up to the equation for Q, our acceleration, if I multiply by 2, is 2t minus g. That's useful. We could also have a look at what friction is. Don't forget friction is mu, which we know is 0.5. R, and we know R has come from our other equation on P. So it should now be possible to substitute everything together. And I'm just going to do it in one step to save space, but obviously take your time with this. So we've got our 4g sine alpha. Sine alpha is 4/5, based on the work we did earlier, minus tension, which we want to find out, so we'll leave that there, minus friction, which is a half of R. Now R is 4g cos alpha, and we know cos alpha is 3/5. And that equals 4a, and we know a is 2t minus g. Not very nice, but all I've done is just replaced all of those parts there. So sine alpha replaced with 4/5. T I've kept the same. Friction I've put it in with what it is, which is a half of R. Put in what R is. And that equals to 4a, and I've put what a is in. So it's just a load of substitutions. When you rearrange that, that gives you 6g equals 9t, in which case t is 2/3 of g. Part B asked us to look at the tension or the resultant of the forces exerted on the pulley. And this is why I always draw the tension arrows coming out of the pulley as well. So we had one tension coming straight down, that opposed the tension for Q, and we have one coming off of the sloped angle. So the force that the pulley feels is acting straight down the middle of the two of them. And that's because they're equal, so it's gonna kind of collapse straight into the middle there. If I just look at that back in the context of the question again, very briefly, the pulley, is up on this top corner of this triangle. We know that that angle at the base there is alpha. So the angle at the top here, this is 90 minus alpha. Now I know, as I just said, that the resultant force, the effect that the pulley feels, is going to be acting halfway down that angle. So that angle there that I've just highlighted is going to be 90 minus alpha over 2, half of the angle. So this is what I need to create, this new blue line that I've just drawn over again there. And so I need to just think about what a little triangle would look like with either of my tension lines that I've got there. Now, the force that we normally have, we're going to keep that on the hypotenuse, so that tension is there. This is my new force, this is my resultant, at least for one half of it, and then there is something else acting on it in the opposite direction, but we'll be thinking about those later. Actually, they cancel each other out in the end. So this angle at the top here, this of course is our 90 minus alpha over 2. And I need to think about what I've called res, or the resultant, is. Well, I'm just going to use trig. That's it. Just going to use GCSE trig, SOHCAHTOA essentially. I have got the hypotenuse and the adjacent. So I've got cos of my angle, which is of course 90 minus alpha over 2. That equals the opposite, rather the adjacent, so the resultant, over the hypotenuse, which is t. This means that my resultant force is t cos 90 minus alpha over 2. Now we've got that for two separate tension forces, so the overall resultant force will equal 2 lots of this t cos 90 minus alpha over 2. I can go out and find out what alpha is. Alpha is 53.13, so on and so forth degrees. Just did that by doing inverse tan, 4/3. And then I can just plug that straight into that equation, and my resultant is 12.4 newtons.